So if you're watching this video, you've probably heard the word stoichiometry in your general chemistry class. You're wondering, what in the heck is that word? Oh my God. There's like an O and an I, and then there's an I and an O, and this word is going to devastate you from now until the end of your academic career, wondering how you're going to spell it and what exactly does it mean, right? So in order to consider this, let's just look at what the word means according to Merriam-Webster's dictionary. And according to the dictionary, stoichiometry, and I actually have the correct pronunciation on here, this is from Merriam-Webster's dictionary. Stoichiometry is, number one, a branch of chemistry that deals with the application of the laws of definite proportions and of the conservation of mass and energy to chemical activity. And definition number two is the quantitative relationship between two or more substances, between constituents in a chemical substances, or the quantitative relationship between two or more substances, especially involving physical or chemical change. So in order to understand this definition, we have to understand what the law of conservation of mass and energy is, right? So this is the law of conservation of mass and energy, and this is actually expanded from the law of conservation of mass and the law of conservation of energy. So we've kind of combined it all into one. In a closed system, the total amount of mass and energy remains constant. That means that matter and energy can neither be created nor can it be destroyed. It's only transformed from one form to another. I think we originally started with the law of conservation of mass, and then thanks to Albert Einstein, he showed us his favorite famous equation, E equals mc squared, which relates mass times the speed of light squared is equal to energy, and that relates mass or matter to energy. So now it's all one and the same, right? So if we conserve mass, we have to conserve energy as well. And so this is actually fundamental to biochemistry as well, in addition to anything in chemistry. And because the total mass of all the reactants must equal the total mass of all the products. And of course, the same has to apply for energy. So let's look at the reaction for photosynthesis. In photosynthesis, 6 carbon dioxide molecules and 6 water molecules are combined together with light energy, and that light energy is captured from the oxidized molecule CO2, and that's absorbing the electrons, and that's producing glucose, which is C6H12O6. That's on the right side of the equation. And as a result, also, we have to balance the oxygen because we have some oxygens left over. We get 6 oxygen molecules, and that's how oxygen is evolved in photosynthesis. And so what we notice is that all of the atoms of on the left side of the equation, there's 6 carbon atoms in CO2. We have to have 6 carbon atoms on the right side of the equation, and so that's how we get C6H12O6. Likewise, the oxygen and the hydrogens have to be balanced as well. So if there is 6 times 2 or 12 oxygen atoms in the carbon dioxides on the left, we add that to the 6 oxygen atoms in the water on the left. That's 12 plus 6 is 18. We have to have 18 oxygen atoms on the right. So we have 6 oxygen atoms in the glucose molecule and 6 times 2 or 12 oxygen atoms in the O2 molecule on the right. So 12 plus 6 is 18. Photosynthesis is now a balanced equation, right? Now, this is also a reversible reaction, right? Plants and cyanobacteria undergo photosynthesis, but also those same organisms, as well as animals, undergo cellular respiration. So we have to do something with the energy we've captured from the sun. And so that glucose, C6H12O6, is now on the left side of the reaction. So again, this is a reversible reaction. And that we breathe in oxygen. So we've got 6O2 on the left side of the reaction. So glucose and oxygen are combining, and they're forming 6 carbon dioxide and 6 H2O, plus we release energy, and that energy is captured in the form of ATP. The energy on the right side of the equation is coming from the bonds that are being broken in the reduced glucose molecule on the left, and that balances the energy of this equation, right? Notice also that if we've got again 6 carbons in glucose, 12 hydrogens in the glucose, and 6 oxygens in the glucose. Those oxygens combine with the 12 oxygens in the O2 molecules on the left side of the equation. That gives you 18 oxygens. That needs to balance with the right side of the equation, the products, and so you get 6 carbons in CO2. 6 times 2 is 12 hydrogens in the water, and 6 times 2 oxygens in CO2 is 12, plus the 6 oxygens in the water, making a total of 18 oxygens. On the right side of the equation, we're now completely balanced. And so balancing equations is particularly important because that's how that accommodates the law of conservation of mass and energy, right? And of course, the energy, I think I've already stated the last bullet point, that it's the energy produced on the right side is breaking the bonds in the reduced glucose molecule on the left side of the equation, right? Now, when we account for everything in each of the reactions, the reaction for cellular respiration is really, it's one reaction that's shown as a net reaction. In fact, it's actually the combination of 10 reactions of the glycolytic pathway plus the pyruvate dehydrogenase reaction producing acetyl-CoA, and 8 reactions of the citric acid cycle fouling acetyl-CoA, and then those 8 reactions of the citric acid cycle produce ATP and water through the electron transport chain, right? So really that one reaction can be summed up into about 20 different reactions, or about 22 altogether, right? So if we account for all the CO2 is going to be produced by individual reactions. This still has to be balanced, even though we've summed up a metabolic pathway, which is all 22 of those reactions, into one reaction that we showed on the last slide. It still has to all be balanced. So how do we balance all that CO2? So we've got 6 moles of CO2 that's produced from the breakdown of glucose in cellular respiration, right? And so this CO2 is going to come from 3 different individual reactions. Number 1 is the pyruvate dehydrogenase reaction. That converts pyruvate to acetyl-CoA. We get 1 CO2 there. We get 1 additional CO2. That's the second CO2 from the isocitrate dehydrogenase reaction in the citric acid cycle. And so that converts isocitrate to alpha ketoglutarate. It produces 1 CO2. That accounts for our second carbon dioxide. And our third carbon dioxide is produced from the alpha ketoglutarate dehydrogenase reaction that converts alpha ketoglutarate to succinyl-CoA, and then that's our third. Now, that's only 3 CO2. How do we get 6? Well, what we also have to consider is that when we break down glucose to pyruvate in the glycolysis reaction, pyruvate is 3 carbons, glucose is 6 carbons, right? So we're going from 6 to 3 carbons. Glycolysis includes an aldolase reaction that splits the glucose from a 6-carbon carbohydrate to 2 3-carbon molecules. That's how we get 2-pyruvate, and then all those 2 pyruvates produce 2 acetyl-CoA, and everything following that cleavage reaction in glycolysis is duplicated twice. So if we get 3 CO2 from the individual reactions, we multiply that by 2, we get 6 CO2 in the final reaction. We get 6 CO2 overall, and that balances our cellular respiration pathway, right? And now let's look at the water. Because we produce 6 CO2, we also produce 6 water, so we have to balance the water as well. So again, 6 moles of H2 are produced from breakdown of glucose and cellular respiration, and this water is mainly produced by the electron transport chain following the citric acid cycle. And so there's 3 primary areas we get water from. The first is the cytochrome C oxidase reaction. That is actually complex 4. That takes 4 electrons and 4 protons and oxygen, and that produces 2 H2O. Right? So there's 2 water. Next, the citric acid cycle produces NADH, and that NADH will actually produce 3 ATP from the electron transport chain, and each NADH contributes enough electrons to reduce 1/2 of the oxygen to 1 H2O, right? And so water, oxygen is really the final electron acceptor of the electron transport chain, and that oxygen is immediately combined with hydrogen ions to form H2O, right? So for every NADH we get 1 H2O. We actually get 2 NADH from glycolysis, 2 NADH from the pyruvate dehydrogenase reaction. We then, in the citric acid cycle itself, we get 2 NADH from isocitrate dehydrogenase and alpha ketoglutarate dehydrogenase, as well as malate dehydrogenase. So that's 5 enzymatic reactions. We get 2 NADH from each, and that's 10 NADH. Now, FADH2 is another reduced coenzyme. This is produced from the succinate dehydrogenase reaction of the citric acid cycle, and we get 2 ATP from FADH2 from the electron transport chain, and each FADH2 also contributes enough electrons to reduce 1/2 O2 to form 1 H2O. So we're going to get 2 H2O from that. So let's add everything up. And so we're going to get, overall, we're going to get 10 plus 2 is 12 water from our NADH and FADH2. So we've got a total of 12 water molecules from these reactions here, right? Now, we're not quite done because 2 water are consumed in the glycolytic pathway. And so this cancels out 2 of the water produced from the NADH and glycolysis. So there goes 2 water right away. That just gives us a net 0. And then 4 water are consumed in the citric acid cycle, and that's by the citrate synthase step, which combines acetyl-CoA and oxaloacetate to make citrate and CoA SH. That's the very first reaction. And then fumarase combines fumarate with water to produce malate. Essentially, that water is added across the double bond of fumarate to hydroxylate the malate, to hydroxylate it and produce malate. And so that accounts for 4 waters. So 2 and 2 is 6, or 2 and 4 is 6. And so 12 minus 2 minus 4 gives us 6 water molecules that are produced. And so this balances our overall net equation perfectly with all of our reactions. So I hope you enjoyed this video. I hope it was useful for you. And feel free to go ahead and hit the like button down below. Subscribe to this channel if you'd like to see more content similar to this. And leave a comment. Let me know how things are going. So thank you for watching.